Good day, everyone. In today's lecture, we will be continuing our discussion in chapter 1, and as you can see here, we are now in this topic. We have representation of integers. So in the previous section, we discussed on how to represent real numbers in a computer. So the very question here is, why do we have a different representation when it comes to the integers, where in fact integers are just a subset of the set of real numbers. Okay, so we will be try to answer that question after discussing this topic. So we will have a brief discussion. We will not be try to have a long discussion about the on how to represent the integers in a given computer. Okay, so the integer n we will be denoted by this letter or symbol, script n, and then just like in the set of real numbers, we have, as you recall, the real number has a integer part and it has also a fractional part. So in the when it comes to the integers, we will be considering only the integer part. Okay, so just like the real numbers, so all you have to do is to divide the integer n by base 2, since we are dealing with computers, and computers has only two words or 2 bit. We have the 0 and 1. Okay, so here we have, uh, as you remember, if you have a 64-bit or a 32-bit, then in the what do you call this one, in the previous discussion, we allot a 1 bit for the sign, and that's what we call the sign bit, and the 63 bits is for the digits. Okay, so when you are given a 32-bit operating system, so you reserve 1 for the sign bit. Okay, so as in the floating point representation, as I've said, we allocate 1 bit for the sign and 63 bits for the digit. So we are considering here a sign representation. There's also a topic with regards to the unsigned. So unsigned meaning not signed, the first digit is, those representation are always positive. But here in this discussion, we will be discussing about signed numbers. We have positive number and negative number. Okay, so there is an approach. This approach is, if you are using the floating point representation, there are some disadvantages. Okay, when it comes to adding integers, and we will see that later in our discussion. But before that, let's discuss this method. This is what we call the two's complement. Uh, and Python is also using this method on how to add or subtract uh, with respect to integers. Okay, so for example, forget about the 64-bit or the 32-bit operating system. Let's focus our attention to an 8-bit computer. So meaning there are 8 boxes. Okay, there are 8 boxes, and we will extend this scenario to 64-bit and to 32-bit or 16-bit operating system. Okay, here for example, uh, escape this one. For example, if you have number 12, uh, in if you represent this number 12 in binary, the result is this one. We know already how to convert a decimal number to binary. So all you have to do is to divide this one, if you recall, But if not, let's try to open our open board, and this one here, this is our goal. 12, the binary number for 12 is this one, using 8 bits. Okay, so 4 zeros, 1 1 0 0. Okay, so if you recall your previous lecture, so for example, if you have illustration here, let's say illustration, example 12, so divide this one by 2, the quotient is 6 and the remainder is 0. Okay, divide again by 2, the quotient is 3 and the remainder is 0. Divide this one again by 2, and then the quotient is 1 and the remainder is 1. Okay, and then I think this is the last one. If you divide this by 2, 1 divided by 2, the quotient is 0 and the remainder is 1. So 12, therefore 12 in base 10 is equal to this binary number 1100. Okay, in base 2. Okay, since we are dealing with an 8-bit computer and there are 4 bits only here, so we will transform this to an 8-bit. So put zeros to the left of this number. Okay, so this will become 0 0 0 0 1 1 0 0. Okay, using an 8-bit operating system. Okay, so this is correct. So how do we represent negative 12? So the problem here is, if we are using the previous discussion, there is a problem when we try to add integers. So let's use this approach, which is what we call the 2's complement, to represent a negative number. Okay, so just in the previous section, if you remember, when s is equal to 0, we have a positive number. When s is equal to 1, we have a negative number, and then after that represent it by using normalized form, and then using IEE 64-bit floating point representation. So that's how you do it in the previous section. So here, to represent negative 12, so all you have to do is this method. It says here that you have to flip all the digits, meaning to say you have to, when you say flip, you have to replace 1 by 0 and 0 by 1, and then you have to add 1 to the result. So that's what we call the 2's complement. Okay, so let's try to illustrate that method using, let's try the screen color, using 2's complement. 2's complement. It says here that we have to flip the digits. So 0 becomes 1 and 1 becomes 0. So from here we have 1 1 1 1 0 0 1 1. Okay, and then you have to add 1. So you have to add 1. We have, sorry, you have to add 1. Okay, so 1 in uh, 1 in an 8-bit computer is, of course, you have to put zeros, 7 zeros to the left of 1, this one here. Okay, 7 zeros to the left of 1, so 0 0 1 1. Okay, and then we have 0 0 0 0 0 0 0 1. Okay, okay, so how many zeros? We have 1 2 3 4 5 6 7. Okay, so if we add, so we have here, starting from the left, we have 1 plus 1 is 2, so we have 0 here, carry 1, so 1 plus 1 is 2, we have 0, carry 1, so 1 plus 0 plus 0 is 1, and then 0 plus 0 is 0, we have 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1. So this is now the representation of negative 12 in an 8-bit computer. Okay, so this is negative 12. Okay, it's using 2's complement. Okay, so as you can see, if you try to use the previous discussion, if you would like to apply the method that we used in the previous discussion, for example, this first digit here is, we know that this is a sub 0, this one is a sub 1, and so on up to a sub 7. And then if you apply the our previous method, we have here a sub 0, this one here, we have the third digit, becomes this is 2 to the 0 1 2 to the 2, so we have here is, we have 0, as we have here 0 1 2 3 4, so starting from 4, we have plus 2 to the 4 plus 2 to the 5 plus 2 to the 6, and the last one is 2 to the 7. Okay, and as you can see, the result would be how much is that? It will be 2 to the 7 is how much is 2 to the 7? I guess we have 1 to 8. Yeah, this 1 to 8. Okay, so this is 1 to 8 plus 2 to the 6 is 64, 2 to the 5 is 32, 2 to the 4 is 16, 2 square is 4. So we have here 20, sorry, so 20 plus 32, let's try to add this one using our using Desmos. Let's try Desmos scientific calculator. So if you have here 128 plus 64 plus 32 plus 16, am I right? Is it 16? Sorry, not that one. Yeah, 16 plus 4 plus 4, and as you can see, the result is 244. So we have 244. Okay, so let's recall it again. So my right, 128, 64, 30, 16, and 4. Okay, so we are on the right track. But as you notice, if you try to convert this binary number to um, decimal, the result is 244, where in fact we have said that this is actually negative 12. Okay, this is negative 12. So if you are going to, what do you call this one, if you are going to convert a number in 2's complement, do not use this method. Okay, this method here. Okay, this one here, do not use this one. All you have to do is to convert this number, by this binary number, to 2's complement again, and then add 1, and then that will be positive. Okay, and then meaning to say that this number uh, came from 2's complement. Okay, so be careful not to convert this number into 2's complement using this method, as what we did in the first lecture, second lecture video. Okay, so this is not correct. Okay, so anyway, what we did is, I'm just trying to explain that you should not do this. No, you should not do this. So what we did here is just to apply the 2's complement and how to get the negative number of a positive number. Okay, so let's hide this one first, and let's go back to our discussion. Okay, and then this is the binary representation using 2's complement, and I guess we are correct. Okay, we are correct. Let's compare. 4 1 0 1 0 0. Okay, so we are correct. So let's hide this one. Okay, notice that if we add 12 and negative 12 using binary, you will have this one. Okay, notice here that there are 9 bits already. We disregard this bit since the last bit, the red bit here, since we are dealing with an 8-bit computer system. Okay, so the first 8 bits, which is all zeros, of course this is correct because 12 plus negative 12 is 0. Okay, so we have to ignore this red bit here. Okay, then using Python, if we are now using a 64-bit operating system, we have the same method. Okay, get the positive number, get the binary representation of that positive number, and then using 2's complement, and then you can add. Okay, so that's how you are going to apply it in a 64-bit or in 32-bit or in 16-bit. The same method as in the discussion that I've done a while ago. Okay, using Python, this is the command, the code. So you have to call the struct package and define a function called into bin, and just type this one. I'm using the IDLE shell in my computer. You can use Jupyter Notebook, or you can use Anaconda and open the Jupyter Notebook or the Spider. Okay, so using the um, Python, this is the representation of the positive integer 12, and this is for the negative 12, and if you add this one, then the answer is 0. Okay, so can verify, and of course we have to truncate, because if we try to add these numbers, there will be all in all a 65 bit, and we have to, as what I've said before, we have to disregard the last bit in the left section. Okay, so there is also another example that that we have an advantage if we have to use the two's complement. Okay, but before that, maybe you are tempted to represent this number, the positive number, positive integer 12, using our previous method, using floating point representation. Then you will have to encounter, you can encounter something in your computation, that there is something wrong in the in that way of representing a integer using our previous discussion. So this is the most efficient way to represent integers. Okay, so this is another example. If you have negative 3, first is you have to get the binary representation of positive 3, get get the 2's complement, and this is the 2's complement. And then also for 5, of course this is positive 5, so you don't need to get the 2's complement here. So if you try to add negative 3 and 5, it's very easy for us, because we are humans. We are able to this is basic for humans to add a decimal number, but for computers, this is how the computer represent. So the answer is, of course, positive 2. For us, this is very easy. So if you look at the binary uh, operation here, the answer is this one. Of course, we disregard uh, this read bit here, and indeed we have 1 0. This is 0 times 2 to the 0, and we have 1 times 2 to the 1. So of course the answer is 2. Okay, so also as I've said, if you notice, we follow the same approach used in the floating point representation. Allocate the leftmost bit to the sign of the integer, then we would not have this property. Try to analyze this statement, this sentence here. Why is it that there's a problem when you are trying to uh, use our previous method? Anyway, if you want further discussion, I have here a what do you call this one, I have here the website. This website here explains more about binary representation of integers. Okay, so you can try to uh, type this URL. Okay, and then search this one, type this URL in the Google browser, and then you will be directed to this page. And then there's so much more about this page, and you will see that this statement here, this statement notice up to this property, you will be able to understand more. Why do we have to use another way or method to represent an integer if you are going to understand this discussion here. Okay, so remember that we are discussing about sign integer, meaning it sign with it means positive or negative. Okay, so try to study this one and you will be able to answer uh, this statement here, this sentence. Okay, so anyway, let's continue. uh, it says here we will not discuss integer representations and integer arithmetic any further. However, uh, we should keep in mind that in 2's complement using a 64-bit operating system, uh, using this method, we can represent up to the lowest number is negative 2 to the 63, and the highest number, the largest positive number, or this one here is the smallest negative number is negative 2 to the 63, while the highest is 2 to the 63 minus 1. Okay, so let's try to analyze this situation. Why is it that the smallest integer is in this form while the largest positive is in this form, 2 to the 63 minus 1, using a 64-bit, meaning 64 boxes all in all, or 64 spaces? And I will ask you a question, of course. If what if you are using a 32-bit? What is the smallest negative number? What is the largest positive number? Using 32, using 16, using 8, okay, using 1 to 8. So let's try to analyze this one first. So let's try to open our open board and let's have another page here. Okay, so discussion. Okay, so let's try to answer first the largest number. Okay, remember that we have 64 boxes. Okay, so if you recall your uh, our discussion before, we know that this first box is for the sign bit. Okay, sorry, for the sign bit. And for this next 11 box, 11 bits is for the exponents. Okay, but anyway, we are not using the uh, floating point representation, but anyway, this is 52. Let's recall this one, 52 bits. 52 plus 11 plus 1, we have 64. Okay, so this is for the real number, but for the integer we will disregard this part here. This let's try to use this one. We will disregard this part here. Okay, we will combine this part here. Okay, so we will combine that one, and all in all we have how many bits? We have 63. Okay, 63 bits. Okay, so notice that the largest number, positive number, since this is a sign bit, this is always 0. Okay, this is always 0, so meaning to say for the largest number we have 0, 1 1 1, and so on and so forth. 1 1 1. Okay, and all in all, this is how many uh, digits are there? Let's try this. Read 1. This is a sub 0, a sub 1, and so on and so forth up to this is a sub 63 and a sub 62. Okay, so starting from 0, we have 0 to 63, or all in all, that's 64 numbers or digits there. Okay, so meaning to say, see, this is positive. Okay, so there's no problem if we use our previous discussion in lecture in part uh, 3b or part 3c or part 3a, that one. But if you are using if you are going to get the negative, okay, the negative this the smallest number, of course the negative one, you will not use the approach that we are using in the positive number. Okay, so anyway, this is 2 to the 0, 1 times 2 to the 0 from here. So we will start here. Okay, so 1 times 2 to the 0 plus 1 times 2 to the 1, and so on up to 1 times 2 to the 62. Okay, 2 to the 62, and of course this will be 2 to the I minus 1. I starts from 1 to 63. Okay, so when I is equal to 1, we have here 2 to the 0. Okay, so anyway, this can be simplified as 1 plus 2 plus 2 square, 2 square, 2 cube, and so on up to 2 to the 62. Okay, so let's apply our formula. This is 1 minus 2 to the r to the n, 2 to the 63 over 1 minus 2, and this is of course 1 minus 2 to the 63 over negative 1. So this is 2 to the 63 minus 1. Okay, and as you have noticed, this is the largest positive integer. Okay, 2 to the 63 minus 1. Okay, so anyway, there is another approach here. As you can see, we have another approach. Okay, remember that there are how many boxes all in all? So we know that this is for a sub 0, a sub 1, up to this is a sub 62, and this is a sub 63, which is the same as this one here, before. If we use this another approach, we know that in our previous discussion, this is we will start here. Okay, this one here. We know that it is a sub 0, 2 to the 0, is a sub 1 for the second term, the second digit, 2 to the 1, and so on up to we'll stop here. Okay, since this is 0. Okay, since this is a positive integer, so is 62, 2 to the 62. Okay, so notice that in this illustration, uh, we replace, since we are dealing with largest positive integer, so of course we will use sorry we will use uh, a sub 0 up to a sub 62, a sub 0, a sub 1 up to a sub 62 to be equal to 1 to get the largest uh, positive integer. So all coefficient, all a sub i's should be equal to 1. So the same method. So what will happen here, or if you try to expand, let's try to expand this one first. This is a sub 0, 2 to the 0 is 1, plus a sub 1, 2, plus a sub 2, 4, okay, up to a sub 2, 2 to the 62, okay. So 2 to the 62 is a very large number. So if you try to use this most calculator, let's try to enter this one. 2 to the where are you? 2 to the 62. So sorry, enter. This is a number converted to this number, okay. Well, anyway, this is this number here, okay. Almost this number, okay. And notice that anyway, it's right here, 2 to the 62, okay. I cannot expand that one. And notice that if we replace all these numbers by 1, we will get this this result here, okay. So the same illustration as we did before, but how about for the smallest, okay. That's smallest, sorry, smallest smallest negative number, okay. Negative negative integer, not number, negative integer. Am I right in largest positive? Let's try to replace this one, largest positive integer. When we say number, it could be a real number, okay. Okay, so how do we represent if you have a negative number, okay, negative integer? So before we extend it to a 64-bit, let's try to have an illustration using 8-bit, okay, before we extend it to 64-bit, okay. So notice in 8-bit we have only 8 spaces, 4, 5, 6, 7, and 8. Okay, so there are only 8 spaces. Okay, so since it is negative, so this is 1 here. Okay, so we have 1 here, that one, and or let me say, let's put a letter first. Okay, this is a sub 0, a sub 1, a sub 2, a sub 4, a sub 5, a sub 6, and a sub 7. And notice that if we try to uh, expand this one now using our previous discussion, we will have this one here, a 2, a sub 0, 2 to the 0. This one here is 2 to the 1, a sub 1. For a sub 2 is 2 to the 2, a sub 2. And then 2 to the 3, to a sub 3. Let's continue this one, 2 to the 4, sub 4, 2 to the 5, a sub 5, 2 to the 6, a sub 6. Okay, we have 2 to the 7, a sub 7. Okay, so since this is negative, okay, so this is negative. Okay, we have here this last term, this one here should be negative. Okay, so this is negative 2 to the 7, a sub 7. But this number here takes two possible values, okay, which is 0 or 1. Okay, so to get the smallest negative integer, our coefficient a sub 0 should be this must be also be equal to 0, this one here. Okay, because if we try to put other than 0, like one of these zeros here is 1, or there's a 1 here, then notice that this is a negative, this is negative, then it will add to uh, this what they call this one, to this term, and we know that this is positive. So if this is always positive, because the value of a sub 2, a sub i's are zeros and 1, and this is our positive number, what will happen is you will not have you will not be able to get the smallest negative number. So for this, it should be that the first term up to this seventh term should be equal to 0. Okay, so this must be all equal to 0, this one here. Okay, and what remains here is we have, and of course we will choose a sub 7 to be 1. Okay, we will a sub 7 to be 1, so this must be 1. So the result will be negative 277, or this is no, not negative 270, negative 2 to the 7, or this is negative 128. Okay, that's for the 8 bit. Now if you imagine if you have a 16 bit, okay, so what would be the answer? Okay, so it's like this is for a sub what do you call this one, this is for a sub 15, right? This is a sub 14. So I guess we have to subtract 1. For this we have negative 2 to the 15, okay, for the 16 bit. And for 32 bit, I guess this is negative 2 to the 31. And for 31, am I right? If we use here, we have 2 to the 63. Okay, 63, so we have 15. No, where are you? This one here, 8 bit. So we have minus 1, 32 to the 31. We have 64 to the 63. Okay, so that's the pattern. So that's the smallest negative integer. Okay, so anyway, I forgot that I will ask that for a question. So anyway, I already give you the answer. So meaning to say, let's proceed. Meaning to say that if it is below this negative number, you have what we call the underflow. And if it is above this positive integer, then you will have the overflow. So if it is below, under; if it is above, it is over. So if it is greater than this number, example this is 8, then we have the overflow. So let's have more discussion about overflow and underflow in this in a little while. So but anyway, in Python, uh, the best about Python is that it can support arbitrary precision integer implementation, meaning to say even if it is bigger than this number, there is an algorithm on how to accommodate those numbers which is beyond 263 and which is also beyond negative 2 to the 63. Okay, but not all. Maybe there is a more extension. It depends upon the programmer if he is able to extend more. But if someday you will be able to extend, although you are using a 64-bit operating system, and then you try to extend the existing number that is beyond this number here, then of course you will be awarded um, for making a program that could accommodate more numbers beyond this one. Okay, anyway, integers of any size can be supported in Python, but it is not true for floats. Okay, so mean to say for real number, example 12.3, bigger than this number, 12.9 to the point blah 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 or whatever, it is not true if you are using a float. But for an integer, then Python can do it. But again, if you can make a program someday, okay, so you will be awarded. So uh, let's try to discuss more about underflow and overflow by using this example in calculus. It says here, from calculus we know that the limit of into the n to the n over n factorial as n approaches to infinity is positive infinity. And if we try to compute this number, if we replace n by 1, 2, 3, then the answer is always float. Let's say, for example, except for 1, maybe if using 2 or 3, we have 3 to the 3 is 27 divided by, how much is that? 27 divided by 3 factorial is 6. 27 divided by 6, so the answer is 4.5. We have a float. Okay, so and many more when n is greater than or equal to 3. Okay, for n is equal to 1 or 2, then it could be the answer is an integer. So it's easier for large n, it will cause an overflow at some point. Okay, and I also put here the solution, see open board. So let's try to use an open board to illustrate uh, this example. Okay, open board and of course Python. Okay, let's make a code, Python code, to generate those numbers. Okay, so let me open my Python, or you can use this one ideally, but I think it is best if we use let's try this one. Okay, so for to implement this one in Python, how should I do this? So maybe I will pause the video first and then try taking uh, this pad here to have more space in this area. Okay, so let's pause this video first. Okay, okay, let's input this example 13 here, this limit, and let's see if we can illustrate how the overflow works. So maybe in your case you can try, or maybe later we can try how underflow works in a Python. Okay, so let's try to illustrate this one. I have here, I will be using my Python shell. So first is, let's try to compute this one, n to the n over n factorial. First, let us call a package, a function. From this package, we have scipy dot special, and let's import factorial, because we will be needing this built-in function in Python, since we have a factorial here. Okay, so it says here that from scipy special, there's an error, cannot name factorial. Okay, I'm sorry, I made a mistake. There's no factorial but factorial, but it should be factorial. Okay, okay, so the don't have an error, so be careful. Our the package that will be that we are calling is case sensitive, and then define this function n to the n over n factorial. So let's use the lambda to define a function n to we have n to the n. Okay, n to the we know how to write the exponent over factorial. Okay? Factorial of n. Okay, so let's see if for some values of n we know that our n will starts from 1, since we are in the sequence. Okay, the idea of the sequence in your calculus 3. So we will start, let's try for some values of n, let's say up to 1000. So for n in range 1 up to 1000, let's print the number I in the range from 1 to 1000 up to 1000. No, the function f of n. F of n. Okay. So and as you can see, it stopped at n is equal to 142. And notice that the range of our n is from 1 to 1000, and it says in the Python shell that it only evaluates up to n is equal to 143. And it says here at the bottom we have an overflow error, an integer too large to convert to true. Okay, so that's how what they call this one, that's how the overflow means in our previous topic, that it's beyond this number, positive number. So as you have noticed, we can we define another function in which it will accommodate more values of n. So maybe let's try another function, the same, but we will modify this this function here. This one here. We will try to modify this function by using maybe multiplication. But anyway, let's try to see what is 143. Let's say float 144. What is 144 raised to the power of 100? Okay. So again, it's an error. How about 143? Float 140 to the power of 142. Okay, so it has a number. Okay, so the problem is in the numerator. This one here, into the end. So maybe let's modify how we define our function. Okay, this one here, lambda function. So let's try this one to accommodate more values of n. Define f of n. Let's say pr equals, let's use multiplication. If now let's try to what do you call this one, finish this first before we go to the open board. For I in range 1 to n, okay, let's try this one, equals n over n minus I, and then return PR. Okay, so for I in range 1 up to say 1001, let's print I comma f of I. Okay, let's have this one. So as you can see here, it already surpasses 143. Oh my god, it works better. Okay, so as you can see here, when it stops until 713. Okay, 713. So what happened? Okay, so the same what do you call this one, the same shell, Python shell, but we have different way of defining a function, but the same formula or the same expression that we are going to evaluate, but different function, and yet this one here, the recent one, works better than the previous definition, or the previous Python code. Okay, this Python code works only from 1 up to 143, but for this function it evaluates up to 700, as you can see here, 713. So what happened? Okay, so let's try to analyze this what do you call this one, this way of coding the expression or evaluating the expression n to the n over n factorial using this way of writing a code in Python. Okay, so let's pause for a moment. Okay, let's continue. Let's try to open the open board. Okay, and then let's recall this one here, illustration. Or shall I say discussion, this one here, Okay, n to the n over n factorial. Okay, so notice that n to the n, the numerator can be written as n times n, this one, n times n times n times n, and so on and so forth. This is n times n times n times, while the denominator can be expressed as n times n minus 1, or shall I say this one here, times n minus 2 by definition, and so on and so forth, 3, 2, 1. Okay, so since this is multiplication, they can write it in this form: n over n times n over n minus 1 times n over n minus 2 times n over n minus 3, and so on and so forth, up to n over 2, n over 1. Okay, so this is the reason why we have, let's try, no, this one here, this one here. Okay, this one, the first factor, n over n minus 1, is 1. N over n is 1. Okay, so n over n minus 1, n over n minus 2, n over n minus 2, n over n minus 3, up to n over 2 times n over 1. So as you can see here, this product, so let's start when n is when I is equal to 1. So when I is equal to 1, so we have this one here. Okay, this one here. When n is equal to 2, this one here. When n is equal to 3, we have here. When up to how about if starts from 1, 20. So when n is equal to 20, we have 20. Okay, so it prints up to, you have noticed here, 1001, up to 1000. Okay, so not included the upper range, which is n, since n minus n is 0. Okay, so we have division by 0, which is we already know that it doesn't work. Okay, so what happens here is when we have here 1, so we have 1, and then this is 1 here, n over n, 1. So when I is equal to 1, so it computes this value here times the previous value, which is 1. When n is equal to 2, then we have here this third factor, and then the latest, or that one, the latest value is 1 times n over n minus 1. So when n is, when I is equal to 2, so we multiplied that value with n over n minus 2. When I is equal to 3, so we have this third factor, n over n minus 3. So the previous multiplication is 1 times n over n minus 1 times n over n minus 2 times the latest up to the last. That's how this multiplication, this expression here, if you type it in the in Python, and then use this command to print uh, the value I and then the function values for a particular number from 1 up to 1000. So as you can see, if we change it to this form, then what will happen is it will take more values than before. Okay, so maybe the built-in function is not quite good in terms of evaluating a larger number. Okay, so however, if we try to make our own Python code and expressing it in this way, then we can accumulate more values. Okay, so there's another Python code that I am going to type here, but I'm going to leave this to you, how to verify that it will work the same as in the previous Python code, but not the first one, but the second one, second one, it will be the same. You have to verify it at home. So let's try to call our package. Okay, let's use SciPy special import factorial. So this will be your assignment, and then write this function. Let's modify the first function, lambda n, the same as before, n to the power to the power of n over factorial. Factorial of n, but we join this word here. Okay, and then try to evaluate, this is your assignment, if it is the same, which one is better. First, the third one, this is the first one, which is 1 up to 143, and then the second one, 1 up to 713, this one here, and how about this third one here, which is better? Try to make a command to print these numbers using this function, new function now. You can change this by f if you want, and of course in your code you can do the appropriate letter so that it will not confuse the Python shell. Okay, so just make just like this one before, and then compare if which one is better, the first one, the second one, or the third one. Okay, that's your assignment. Okay, so anyway, let's hide this one. Our next topic will be on chopping and rounding. Okay, so I'm going to upload this video. Thank you so much for listening. I hope that you learned something from this lecture video. Okay, so escape. Let's